Namaste, namaskar, and good morning. Welcome to this course. First of all, I would like to thank Dr. Raghavendra and Dr. Narasimhadhan for working with me and inviting me to present this course sponsored by GIAN. I'm also grateful to GIAN. This is the fourth course I'm giving under GIAN, so somebody must be liking this kind of material. I have given two courses on IITs and NITs, and this is the second time I'm giving. The first time was at IIT in Allahabad. It's my pleasure to be here, close to my hometown, which is Mandayam. So I'm from this state, but it's hard to give the entire course in Kannada, so we will use English. But in addition to English, there will be a lot of mathematical equations, hundreds of equations. But you have PDF files of my lectures, I presume. I hope you have downloaded those. If you don't have, please contact Dr. Raghavendra and download my notes. The notes are extracted from my textbook on biomedical image analysis. We tried to get that book through CRC Press, but it didn't work out. But I have special permission from CRC Press to share those notes. The equation numbers, figure numbers are exactly the same as in the book, but the text is reduced. All the equations and tables and figures from the book are present in these PDF files, marked chapter 1, chapter 2, and so on. So you will have all of this material with you, but you may want to write down a few points so that you can maintain attention and jot down a few points. The course is intensive in the sense we have many equations and algorithms before we can look at the results. And I would urge you to go through those equations and procedures later on at your own convenience to get a good handle on the process. My book has 12 chapters, but we will cover only 6 chapters in detail and a couple of other chapters in a quick survey of texture and oriented pattern analysis, depending upon the time available. And then towards the end, I'll have 3 seminars related to our research projects. So you will see some practical applications from our own research. Even in these chapters from the book, you will see many examples, some using test images and some using biomedical images related to my research projects. I work with a number of graduate students, very smart grad students, many of them from India, and also with many biomedical researchers and medical researchers, radiologists, pathologists, oncologists, and so many other specialty researchers in medicine, and it's been wonderful to gain from their knowledge, and I'll try to pass on some of that experience I've gained over to you in these discussions. The original plan and proposal to GIAN was for me to give 40 hours of lectures, 40. So you have to bear with me. The last day I'll have to leave a little early. So this week I would ask you to extend the timetable to about 5:30. So we will have 5 hours per day of actual lectures, not counting the breaks. And then we will see how it goes and manage the time. Okay? Any questions or concerns? Are you able to understand me? It's clear? You may want to come to the front because there will be a lot of details and equations. That's the straightforward title. If you just want to know the technical material, it is digital image processing, but we are dealing with applications to medicine and biomedical engineering applications. So I have called my book Biomedical Image Analysis. I have added a few more words here to make the title a little broader and include a few other topics. We will have brief discussions on what is radiomics? That's not my main area of research, but it's a new topic where a few other branches of science and engineering are brought in. Medical informatics is well established. It's just another name for the application of information and communication technologies in medicine. So these names, these three words were included to make the scope of the course a little broader and have a better appeal. Essentially, the topic is computer-aided diagnosis. How do you use computer engineering or electrical engineering and signal and image processing, pattern classification, pattern recognition methods to improve healthcare? So the term that's been accepted over the past 20, 30 years is computer-aided diagnosis, not automated diagnosis. I avoid the term AI. I don't like artificial intelligence. This is real intelligence. When you say artificial, it has different connotations, especially in medicine. You don't want anything artificial in medicine, in food. So I'll completely avoid that term. But what is called AI nowadays includes almost everything done with computers. So you can call this AI if you want. Another term used is machine learning. I don't use that term too because it doesn't say much. Machine, which machine? Learning, what are we learning? Whereas if you say digital image processing, it's clear. As engineers and scientists, we should use precise terminology. You could say this is engineering for improved healthcare. So we are applying engineering to achieve better healthcare, better well-being. That was the topic of my research many years ago, 50 years ago, with Professor I.S.N. Murthy at the Indian Institute of Science. Your professors, Dr. Raghavendra and Dr. Narasimhadhan, are also from IISc Bangalore, and I graduated from there, got my PhD many years before them. You got some years in my bio introduction, so you can work out the details as to what the years could be. I've been with the University of Calgary, and I've been fortunate to have had the opportunity to collaborate with many medical researchers, and that has helped in my own understanding of the topic. So that's the textbook published 20 years ago. The publishers asked me to update the book earlier, but I didn't do that. It has 1,300 pages. I didn't want to read it again. But after retirement, they asked me again, and I said, okay, let's do it. And we are working on the second edition with a co-author, one of my research associates, Benjamin Lovi, and hopefully that book will come out next year. And then I will make that available here. So here's, from the cover of the book, an illustration as to what this is about. What is this matter, this subject about? There are various stages of biomedical image analysis. First, of course, you must acquire the image. Image acquisition or imaging. I will not be getting into that. That's the first chapter in the book. And I had sent a message asking you to read through the first chapter. It's just a story, so you can read it and look at pictures. And some of that is basic college physics material. So I'm not going to go through that. Let's say you have acquired the image somehow, or somebody has acquired an image and you have it on your hand. You are given a problem. Like this is a part of a mammogram, X-ray image of the breast. And there is a tumor there. Only that part is shown. But the full mammogram is much bigger. This is the 1,000 by 1,000 pixel portion of a 4,000 by 4,000 pixel image. Perhaps you can see that there is, let me see. Okay, here. There is a relatively dense portion, brighter portion, and that is a tumor. So the problem in computer-aided diagnosis here is to detect the tumor, get its boundary, and measure some characteristics, measure some features, extract features, and then try to say whether that tumor is benign, that is not cancerous, or malignant, that is cancer. So first we need to enhance the image. Perhaps there are some artifacts, it's not sharp. So you need some enhancement algorithms to clean up the image and improve the quality. So filtering to remove artifacts, improve contrast and visibility. That's not shown here. And next is to detect the region of interest, what is called image segmentation. Break the image into parts, but in medical imaging, we don't break the image into multiple parts like every piece. We're not interested in every piece here, but we want to detect specific parts like, is there a tumor? Are there calcifications, or is there something abnormal? So for that, we have developed a method where there is multi-level thresholding. First, the image is filtered, and then you find iso-intensity contours, and then find a family of contours that encloses other smaller contours within and get the biggest contour. And the blue line here is the contour obtained for that region automatically. But there are a few other blue regions here that pass the test. So those are false positives. So initially, we want to keep a high level of sensitivity of detection and allow some false positives, and later reject the false positives and keep the real region of interest. So here is the this red line, but the blue line is the actual contour drawn by a radiologist without looking at this result independently. So it's a good approximation, not perfect. These spicules have not been gathered, but the undulations have been captured, and the false positives. So we have other methods to reject false positives. We will go through the details later on. And then once the contour has been obtained, here I'm showing the contour drawn by the radiologist, we perform analysis of shape. Is the shape smooth or rough, or is it spiculated, like having finger-like protrusions? And that was an idea given by Dr. Desertel, the radiologist with whom we collaborated. And we characterize that. The red portions are convex portions, curving outward. And the green portions are concave portions, curving inside. So that gives us an important measure of what is called fractional concavity. So it is shape analysis, but specific to the analysis of tumors. I'm showing a tumor in a breast image here, but it's true in most of the types of tumors in other parts of the body. Malignant tumors keep expanding, so they have these protrusions. If there is a protrusion, between two protrusions, there will be a concave part. But if it is round, there is no concave portion. So that is shape analysis. So once you extract the features, this is one feature. You can compute many other features for shape, texture, and whatever else you think will help in separating the categories. Then you just put them in what is called a machine learning algorithm, what I would call pattern recognition and classification, and find a boundary and classify. So classification forms the sort of end part of this process. We will not go into pattern classification algorithms. That's a different subject by itself. So here we will concentrate in this course on how do you represent a digital image for processing, how do you apply filters. So we will go through some basics of linear shift invariant systems and transforms. Many of you would have seen that in 1D, maybe even in 2D. I'll ask a couple of questions later. And then specific methods to extract, to detect objects and to extract features for biomedical applications. So that is what we will do over the next week or so, 2 weeks. Okay? Now, I have been teaching this course on digital image processing or biomedical image analysis for more than 40 years. And the emphasis has changed over the years. The illustrations I have used have changed. But the basics remain the same. It's DSP, or digital signal processing, in 2 or 3 dimensions, or call it digital image processing. To get a good understanding of this, you need a good background in signals and systems and transforms, first and second year engineering material, electrical engineering, and digital signal processing would help, not necessary, but it'll help. And then digital image processing, we will go through the basics of some of the portions. I presume most of you are engineers, is that right? Yes. Anybody who is not an engineer? Okay. All electrical and computer or any other? Medical engineering. But you have done signal systems, transforms. Anybody without signals and systems and transforms background? That's good, that's good. Digital signal processing, have you all had? Anybody without DSP? Oh, that's good. So some of the introductory parts I may go a little faster then. So this is the first chapter, but I will not go through that. Is that okay? Any questions or concerns you want me to do something differently? I call the second chapter image quality and information content. I didn't want to call it signal processing, image processing, and so on, but in the context of biomedical image analysis, we will use signal systems, transforms, and so on, first to represent images and then to analyze them to understand their nature. What do you have in this image? What is its quality? And what kind of information is present from a statistical and information theoretic sense before we start to filter and process and analyze them. So it is, you can also call it image representation. But what is important in medical image analysis is first you must understand the nature of the image. What is present there? What do you want to detect? What do you want to do with it? And is there adequate information? And does the image have adequate quality so you can proceed with the further steps? So quality improvement, quality analysis and quality improvement is an important initial step. Unfortunately, regardless of the quality of the equipment and the cost of the equipment, images are often acquired with poor quality. Something happens, something goes wrong. The patient moves, or there are so many factors in a practical setting like a hospital. In a lab, you have better control. In a hospital, in a clinical setting with a real patient, you don't have much control over the situation. So there are several factors that affect image quality and the information content that you want to extract and analyze. So a good understanding of such factors and characterization of that information and quality is important. So then you can design appropriate image processing techniques. You need to remove the degradation, you need to remove the noise and artifacts and retain the desired or required information. Can this be adjusted, please? We're losing a little at the top. If you can bring that down. So, the problem with this chapter, with this material, is how do you characterize quality? Quality is subjective, but in scientific and engineering analysis, we want to be objective. So there are two opposites that I'll mention often: subjective, objective, qualitative and quantitative. As scientists and engineers, we want to be objective based on measurements and rules and so on. And to do that, we have to have quantitative information. Subjective is just giving an opinion, oh, this looks nice, or there is something here that looks to be rough. But how rough is it? How smooth is it? So that's the difference between subjective, objective, qualitative, quantitative. So given that quality is subjective, how do you quantify it for objective analysis? So that's a contradiction right there in terminology and in concept. But there are several notions in science and technology that help us here. Information is multifaceted and can be analyzed in terms of statistical, structural, perceptual, semantic, and diagnostic connotations. Statistical, you take mean, standard deviation, skewness, kurtosis of some probability density function, or PDF. And structural, what is above, below, under, behind, and so on. Perceptual, what do you see there? What does the radiologist see in terms of visual perception? Semantic, what is the meaning of thing? of that thing you are seeing, or the radiologist or the cardiologist is seeing, in that application specific. And then diagnostic in medical diagnosis. What does it mean in terms of the diagnosis for the patient? In imaging, there are a few basic issues, such as accessibility of the organ of interest. You want to image my brain, but I have a thick skull. We all have skulls. So how do you get a good image of that, and how do you get an image of the vessels, blood vessels within the brain? It's difficult because of the presence of the skull. So the brain is protected by the skull. The prostate is at the base of the bladder near the pelvic outlet. Accessing is difficult. So there are many such situations. Sometimes X-ray contrast is used. A dense material is injected into the body to increase the density within the blood vessels, but that carries some risks. Most people will tolerate that, but some could have some allergic reaction or worse. There is variability of information. It's not one thing. A tumor doesn't look like one thing. There are many, many possible variations of shape, size, and texture, and so on. So biological systems and entities exhibit great ranges of inherent variability. There are multiple categories, but within each category there are variations, and that makes an overlap, that causes an overlap. So it's not like benign is there and malignant is here. Between them, there is some overlap. So how do you draw a boundary? So that variability in biological entities makes pattern classification more difficult. The distinction between a normal pattern and an abnormal pattern is often clouded by overlap, no matter what you measure. So you need multiple measurements, and hopefully somewhere you will find some separation. When multiple abnormalities need to be considered, cancer of this type, cancer of that type, disease of this type, disease of that type, then it becomes even more complex. Imaging conditions and parameters affect the quality of the image you acquire. The X-ray dose, or the kilovoltage KVP, or the MAS, the amount of current you put in, they all affect the contrast and visibility and characteristics of the images. Patient positioning and projection, am I standing like this or like this? So all of these affect the nature of the image and the particular object you're interested in, like a tumor or blood vessels. So these cause variability in the information. So the algorithms you design need to be adaptive and flexible to capture such information. Contrast that with manufactured goods. So this is manufactured, and it will have this shape coming from the factory. There could be some small variations and maybe some damage in transportation, but mostly it's like this. But not all of these remote controls will have the same shape and size. But from the manufacturer specifications, you know what it is, but not what is inside my body or yours. So for example, most malignant breast tumors are irregular and spiculated in shape, having these protrusions because the tumor is expanding. Benign masses are smooth, they are contained, almost encapsulated. But some malignant tumors may not have these protrusions, or they may be some small variations in the contour. A tumor may present a rough appearance in one view, but not in the other, because the protrusions may be in some directions, but not everywhere. And that is in 3D, but you may get a 2D image. So when you analyze shape, you need to consider that. A radiologist will say this is smooth shape, this is rough shape. But what is roughness? It could be anything from over a scale that is not defined. So how do you bring it to something between 0 and 1, or 0 and 100, and put a number? So these are issues that cause some difficulties. Overlapping patterns caused by ligaments, ducts, and various tissues may confuse detection, and overlapping of one vessel here, another here, and some ligaments here may cause a spiculating pattern that is not a tumor, but because you only have a 2D image, it looks like something suspicious in one image. But if you have another projection, that will clarify. If you can get 3D, that's better. But in some cases, like breast imaging, 3D is difficult because of X-ray dose and other considerations. I use breast imaging quite often because that was one of my major research projects for more than 30 years. So there are a number of examples of mammograms and detection of various parts in mammograms for the diagnosis of breast cancer in my examples. But similar issues and concepts are applicable in many other situations of imaging. It is possible to get multiple images, but you always have to consider the radiation dose in X-ray imaging. In magnetic resonance imaging, it's a cost. You have to pay. In Canada, it is free because we pay a lot of tax. It's not free. Tax is taken right away before the money comes to my bank. But for me to get an MR image, even with all the specialist recommendations and prescriptions, I may have to wait for 6 months to a year because it is free. Here, you pay money and you get it right away. But you have to pay a lot of money, I presume. MR imaging, not many people can tolerate being in that, like a chamber, and there's noise and cost. So all imaging procedures have some limitations and difficulties of access. There are artifacts that come up in medical images. Physiological systems are dynamic and active. My heart is beating, you can't stop that. I'm breathing, but I can hold my breath for a few seconds, but I can't hold my heart. So one will interfere with another. They're interconnected, but if you want an image of only one of them, that among multiple interconnected systems, it is difficult to control all of them. You may control one or two, but not all. And that only with adults in good health. Pediatric cases and adults who are not in good health may not be able to cooperate when asked to do some certain maneuvers or positioning. So cardiac activity, blood circulation, peristaltic movement of things within your gastrointestinal system, they are not under one's volitional control. So one should pay attention to these factors. Energy limitations in X-ray imaging, the dose, the voltage, the kilovoltage, and the amount of current or tube current that is, or exposure in milliseconds, all of those things affect contrast and detail visibility. You have to adjust those depending on which part of the body you are imaging. But low energy X-ray photons are absorbed more readily than high energy photons of X-rays. So at the skin level, there is a lot of absorption of the low energy X-rays. You have to use a filter to remove such unwanted part of the radiation spectrum. A compromise is often required between dose and image quality. Increasing dose may give you better quality of the image, but the patient will accumulate the effect of such increased dose. So patient safety is important, the protection of the subject from electrical or other types of hazards, radiation, electrical, and that is very important. And ethical approval by specialized societies is also required. All of our projects have to go through approval by multiple committees in at the university and the hospital and the cancer board and so on. The main aim is to minimize the risk and discomfort to the subject and maximize the benefits to both the subjects and the investigator. That is an essential requirement in the application of technology to medical situations. So let's look at characterization of image quality. So there are many types of information you can gather from an image, but what are these? And how do you measure and represent them? The idea of getting measures is to separate categories and also to analyze images. And changes in the measures may be related to some of these factors. Comparison of images generated by different imaging systems You get systems from Philips and Siemens and so on, and you want to get the best. So you take a certain test object and take pictures using all of them, and then make some measures. You can look at them and say, oh, this is the best, but can you back it up with some measures? Comparison of images obtained using different imaging parameter settings. Once you select one type of imaging system and it is available to you to test, there are so many knobs and parameters that you need to test, to adjust. And then you can obtain multiple images of the same test object, not the patient, some test object, and compare and figure out which one is the best. Comparison of the results of image enhancement algorithms. Look at a textbook, mine or any other book, and there are many, many algorithms for image enhancement, contrast enhancement, noise removal. So which one do you want to use? So you again compare before and after and make some measurements. Assessment of the effect of passage of an image through a transmission channel or medium or storage where there could potentially be some loss. Image compression, if you do with loss, then you need to know how much has been lost. So first is initial step if you have an analog image, but nowadays you don't have that. Most of the images are acquired digitally to begin with. There is already some loss there. You should keep that in mind. When you take a film image, we call it analog, but there are these silver halide crystals or some form of material that has a certain limit in resolution, but that is usually very small. The pixel size is much bigger. But if you have a digital image acquisition system, then you don't have to worry about sampling. And perhaps quantization also matters. What you get out of your digital imaging system may still be, or will typically still be, an analog signal from a CCD or some kind of a device. An X-ray, there are solid state X-ray detectors now. So there will be an analog output. And that needs to be sampled and quantized, or quantized rather, not sampled. So these cause some loss of information. Basic Nyquist rate and Shannon's theorem. If you have a band-limited signal with a frequency of the fastest component or the maximum frequency being FM in hertz, you should sample at minimum 2 FM from basic 1D signal processing. The problem in image processing is you don't know the bandwidth of the image. How do you measure that? In the case of analog signals, you can put them through some sort of a spectrum analyzer analog and know what is the range, or somehow you know the maximum frequency present from experience. In the case of images, it is more difficult and we just go and sample. And if there are artifacts, then you have to increase your sampling rate. So sampling is modeled as a multiplication of the analog signal with a periodic train of impulses, and multiplication in the time domain or the space domain is equivalent to convolution in the Fourier domain or the frequency domain. So the spectrum of the signal or the image is convolved with the spectrum of the sampling signal. And that creates multiple copies. And you don't want them to overlap and cause aliasing errors. So that's why the sampling frequency must be at least double the maximum frequency present. So the Fourier spectrum of the sample signal is periodic because of this convolution with an impulse train. So that is something we have to remember in image processing using transform domain techniques. That the transform domain is periodic, and if there is aliasing error, you will see it in the borders of the high frequency zone. If the aliasing error is severe, that will affect the low frequency, mid frequency ranges also. A sample signal has infinite bandwidth due to this repetition. Of course, we don't look at all of them. We take the baseband or the central copy. FM equal to plus minus Fs sampling rate divided by 2. If there is aliasing error, then you cannot fix it. So when you acquire an image in the digital form directly from some medical imaging device, if aliasing is present, there's not much you can do about it. except take only the low frequency part where there is no artifact. So correction after the fact is nearly impossible. To recover the signal back from the samples, you use interpolation. You take only the baseband copy of the sample signal in the frequency domain, and putting that window is equivalent to convolution with some kind of an interpolation function. So if you use a rectangle function in the frequency domain, the corresponding function is a sinc function in the time or space domain. And that operation, multiplication in frequency, is convolution in the time or space domain, and that becomes interpolation. I'm going through this fairly quickly because you have seen all of this in 1D DSP. So in 1D DSP, you use an anti-aliasing filter. You cut the bandwidth of the signal to half the sampling frequency you want to use. We can't do that with digital images once it's already digitized. And with analog images, how do you filter? It's possible. You can blur the lens, that is filtering. You can do a few things, but there are limitations there. It requires prior knowledge of the signal's bandwidth. In real-life applications, you don't know that. It is hard to estimate the bandwidth of the signal. So here is an example. Could you turn these lights off, please? Only these at the front. That also. Yeah, this is okay, I think. That's okay. I think we can leave it like this. I may use the board, so thank you. So here's my picture when I was much younger, and that is at 225 by 250 pixels, not high resolution, from an ordinary camera, TV camera. It's already sampled, but if you were to use a lower sampling rate, this has only 112 by 125 pixels, 56 by 62, and 28 by 31 pixels. I downsampled further and further. So as you go to very poor resolution, larger pixel size, and I'm displaying them all to the same size, you see these artifacts of the pixel blocks. There's also some thresholding that happens. This part is highlighted, and this part is highlighted, which is the tumor. So filtering and downsampling is an important step in the detection of objects. That was not the purpose here. This was to show the effect of larger pixels versus smaller pixels, or finer sampling versus coarse sampling. So obviously there is loss of information and quality. Next, you have to quantize the value that you get for each pixel from a CCD or whatever you're using. And typically, you quantize with 8 bits per pixel, but in medical images, you may need 10 or 12 bits, or maybe even 16 bits per pixel to get better dynamic range and detail within the dynamic range. So if you use n bits per sample and positive integers, you have values in the range 0 to 2 to the power of n minus 1. So if you have 8 bits, you have the range 0 to 255, known as gray levels. It is important to map the quantization function properly to the dynamic range of the signal. Otherwise, you may be taking only a small portion, and you may lose information outside the range of the quantizer. So the mapping of the range of variation of the analog signal to the dynamic range of the quantizer is important, and also the decision levels of the quantizer should be optimized with respect to the probability density function, PDF. So I'll use PDF. So it is not a PDF file or not postdoctoral fellow, it's probability density function. A popular method is Lloyd max quantization, where you take the range R min to R max and have a number of these levels that are decision levels, and a number of output levels of the quantizer that are the output quantized levels. And you need to map them. I'll go to the picture here. Sorry, so where did it go? So this is the range of the input, and these are the decision levels. These are the quantizer output levels. And that's the probability density function of the input signal. If it is uniform, then you could divide this equally. The distance between these levels is equal, and the quantizer output level will be in the middle. If it is not uniform, such as a Gaussian like that, then you may want to put more output levels with finer spacing in one part and not the other. The error is given by this equation. R is the input variable, this. QL is the quantized output. There are 0 to L minus 1 of them. And within this, you multiply this error, multiply with the probability density function, which is this, and that's the error. And you want to minimize that. So when you go through the minimization process, you get a suitable quantized output that is optimized to the probability density function of the input variable. So depending upon some assumptions you make, the quantized output level is the centroid of the portion between the two levels. The quantizer output value depends on the PDF, so it is not in the middle, but it will be shifted depending upon the probability density function. If the PDF is uniform, it is simply in the middle. And the decision levels are also in between, exactly in the middle between two successive quantization levels. So that is a simple case when the input per PDF is uniform. So what do these numbers mean? It depends upon the application and the modality of the imaging system. If you are using X-rays, if you consider lung tissues, the density in grams per centimeter cube is less than 0.001, mostly air in the lungs. And the X-ray attenuation, I don't have a number, I searched, couldn't find a number, is very low. The Hounsfield units in computed tomography, CT imaging, is in the range of minus 700 to minus 800. So the output values that you get from these imaging systems have some relationship with a physical or physiological entity. They are not just numbers. If you just convert them to a JPEG image or TIFF or some image and scale it to something, then you lose that information. So in medical imaging, it is important to maintain, for example, in CT images, keep the values in Hounsfield units. The optical density, I'll talk about that later, that is high in the film image. The gray level is low because it is dark in the image, appearance is dark. Liver in an X-ray image has a density of 1.2, a lot more than lung. So the X-ray attenuation coefficient is much higher, 0.18 centimeter inverse. Hounsfield units will be in the range of 50 to 70. Most of the abdominal organs are in the range of 50 to 70 Hounsfield units in CT images. The optical density is medium, gray level is medium, appearance in the image is sort of gray in between. The higher end we have bone with a density of 1.9 grams per centimeter cube, and bones will absorb more X-ray photons. So the attenuation coefficient is higher. I couldn't get a number. The CT unit is about 800 to 1,000 Hounsfield units. The optical density in an X-ray image will be low in the sense it's a bright part. Gray level is high and the image appearance is white or bright. Calcifications in breast images also will have characteristics similar to bone because they are deposits of calcium. So quantization, what happens if you have poor quantization? This is my picture again with 64 gray levels. The original I showed had 256 gray levels. This is 64, 16, 2, and this is 1 bit. 2 gray levels, black and white only. So again, interestingly, the tumor is caught there, but that was not the intent of this exercise. There is a highlight here on my head, on my forehead, because of that part being bright due to some light they used when taking these pictures. So you can see the loss of quality when you reduce the number of bits, 8 bits, 6 bits, 4 bits, and 2 bits. No, sorry. Now 6, 4, 2, and 1 bit per pixel. So you see these false contours here. And if you pay attention, you may see that there too, we may not see, but a radiologist will catch such artifacts. So how do you represent the digitized image now for further analysis and processing? There are 2 ways of looking at the image, and this is a source of confusion in programming. One is the array format, and the other is the matrix format. If you use MATLAB, everything is matrix. Even one value is a 1 by 1 matrix. A vector is an n by 1 matrix, or m by n, whatever matrix. But the matrix notation of counting rows and columns and the array notation of indexing are different. So normally we write an image as fxy, or pij if you want, but in the continuous format, we will use both continuous and discrete notation interchangeably, depending upon what is convenient in a particular setting. A digitized image, FMN, may be interpreted as a discretized version of fxy, or as a matrix. An m by n matrix has m rows and n columns. Its height is m and width is n. Numbering of the elements starts with 1, 1 at the top left corner. So this is where there could be some confusion in programming. This is a matrix, first row, second row, third row, first column, and so on. And the origin is there. There is no 0, 0, so it starts with 1, 1. Whereas if an image is given to you and you're using array coordinate system, you assume that the image is placed in the first quadrant. This is 0, 0. So you have F0, 0, and that pixel. You may want to center it here, but I put it there. So this is 0, 0, 1, 0, 2, 0, and so on, 0, 1. So the indexing, this is 0, 1, but that is to 1 there. So which notation do you want to use? One has to be careful about that. You cannot mix the two. As long as you stick to one, you will be okay in most cases.